Hello and welcome to another video. In this video we're going to be working on most stones removed with same row or column. And in this one you have a 2D plane and you place n stones at some integer points, and each coordinate point may have at most one stone. A stone can be removed if it shares either the same row or column with another stone that has not been removed. So given an array of stones represents the location of the stone, return the largest possible number of stones that can be removed. So this thing, basically, if we label, or if we number these stones, we can say we can remove stone 6 because it shares a point with stone 4 that hasn't been removed. So we'll remove stone 6. Then we can remove stone 5. So if we say this is gone, we can remove stone 5 because stone 5 shares a point with stone 2. So we can get rid of that one too. And then we can get rid of stone 4 because it shares a point with stone 3. And then we can get rid of stone 3 because it shares a point with stone 1, I guess. And then we can get rid of one of these as well. So let's say we get rid of this one because they both share the same thing. And then you can never get rid of the last stone because there's nothing else. Okay, so let's look at the second example. Same kind of thing. So if we just number them. So it actually turns out like the order you get rid of them doesn't really matter. So we can just look for similarities. So like these share a point, so maybe we'll get rid of this one. And then let's see what else shares a point. So these share a point, so we'll get rid of this one. And these share a point, so we'll get rid of this one. And that's all you can do. And it'll kind of make a lot more sense why it doesn't matter which way you remove them. Once I explain it a little bit more. And then here there's only one, so like I said, you can never remove the last one. So basically you see that like these stones are connected where if two stones share a row and a column, they're like connected. So what we can do is, let's actually just get rid of all this. And let's take this example 1 and let's number the stones one more time. And now let's actually write these out as nodes. And then whenever there's a connection, we'll connect them. So we'll have like 1, 2, 3, 4, 5, 6. Okay, so you could see that 1 and 2 are connected, so we'll just connect them. You can see that, what else is connected? So 1 and 3 are also connected. And then 2 is connected to 1, which we already have, and 2 is also connected to 5. So we'll connect like this. And then 3 is connected to 4, and it's also connected to 1. And a bunch of like, this isn't necessarily the case where, you know, only a couple nodes will have some number. Like you can have every stone start with row 0, for example. You know, like the first number can be all 0, and then that means they're like all connected. Okay, and then 4 is connected to 3 and to 6. But basically this is all you need. So you can kind of see like this whole thing is connected now. And it doesn't really matter if there's more connections, like there's this, it doesn't really matter. But once you know everything is connected, you can see how like you can basically remove a stone if there's another stone you haven't removed that it shares a connection with. So you can see like once everything is connected, no matter if there's more connections, you have kind of like a circle. And then it doesn't really matter which one you remove first. Like I can remove them in this order, like 3, 1, 2, 5, 6. I can go 6, or I can go 4, 6, 5, 2, 1. You know, it doesn't really matter how you remove them. Well, I guess it does to an extent, right? Like there are some bad ways. Like for example, if you remove 1 and then you remove some other one, that might be problematic. Like if you remove 1 and then you remove 4, then like 3 is stuck by itself. But as long as you just say like, if everything's connected, I'll just remove them in a circle. And so I can remove, we can write that down. So for a group that is connected, just remove them in a circle and you'll have one stone left. Right? So we can basically make all these connections, and for every connected group, if the group has X stones, that means we can remove X minus 1. So if we had more groups here, like let's say we also had 7 that was connected to 8, that was connected to 9, and then with like 10 by itself. So for this group, we'd be able to remove 5. For this group, we'd be able to remove 2, and then we can't remove anything here. So that's kind of the idea. What we can do is we can just take our stones and group them together. And then for every group, we can just remove x minus 1 nodes. So all we have to do is just figure out like what are all the groups and then remove x minus 1 nodes. And so you can think about it really quick. What algorithm do you know that lets you group things into groups? And it's going to be union find. And so all we're going to have to do here is we're just going to have a dictionary of rows where we have a row value and columns where we have a column value. And it doesn't matter how you connect these. So for example, I connected them in the circle, but it's totally fine to say like, okay, let's just do this instead. 1 connected to 2, connected to 3, connected to 4. Like this doesn't matter for a union find. You can connect them in any way you want. This is still one group. So what we can do is we can just have a dictionary of all of our rows, like row values, and then whenever we hit a stone, we'll just check, is there one with the same row and is there one with the same column? And if there is, then we will connect them, and if there's not, then we will put our stone in there. So let's kind of walk through this example with that really quick. So for rows, we'll have nothing to start, and then for columns, we'll have nothing to start. And let's say these stones are numbered like this. So we're going to go to stone 1. So it has row 0. There is no row 0. So we're also going to say for row 0, let's put in stone 1. And then for column 0, let's put in stone 1 because we don't have anything. Okay. Now for stone 2. So for row 0, there is stone 1. So we can connect stone 1 and stone 2. So we'll make this connection. And then for column, the column is 1. We don't have anything. So for column 1, we'll put in stone 2. Then stone 3, so row 1, we don't have anything, so we'll put it in. And it's column 0, which is stone 1, so we'll connect it like this. Like I said, it doesn't matter if we connect 3 to 1 to 2, whatever. If we connect it to a connected group, it doesn't matter how. Okay, so 4 has row 1, so row 1 is 3, so we'll connect like this. And then column is 2, which we don't have anything. So, and then 5 is row 2, which we don't have anything. And the column is 1, which is 1. So that'll be connected like this. So, and then that's that. And then for 6, it's 2 and 2, which is 5 and 4. So we'll connect 6 to 5 and 4. Once you connect it to one of them, it'll basically be all union. But you see, like, it doesn't matter how you make these connections. As long as you know this whole thing is connected, then you're fine. So we're essentially going to union this. And then we're just going to call the find function on every node. And the find function will tell us the parent. So let's say in a union find, like every component has a parent. So let's say this is the main parent. So we're going to call the find function on every node, and the only nodes we're going to care about is where the parent is its own parent. So when find of x equals x, those are the nodes we care about because we don't want to have like duplicate things. So for every group there will be a parent of that group, and then when you call that on that node, it will return that value. So the parent of this node will be 2. That means if when we call find then all of these, it will give us 2. So we'll ignore those. But when we call find then 2, it will give us 2. And then all we have to do is just figure out like what's the size of this group. So we're going to add a size to the group, and I'll kind of show you how in the union find. And then we're just going to say, okay, if this is the parent of the group, how many nodes are in that group? And then we're going to add whatever the size of that group is, minus 1. And then that's basically it. So it's just you have to be comfortable with union find and manipulating it a little bit. So if you haven't done any union find, I'd look at some easier problems, but this is basically what we're going to do. So hopefully that makes sense. So let's take a look. So here we have a basic union find where I just added a size. And the size of every group starts out as 1 because every node is by itself. So that's what we did here. Then this is just the basic union find where it's a union find with path compression. And then so this is the stuff we added as well. So basically when we get the parents of the nodes, if they're the same, they're already connected, so we don't have to do anything. Otherwise, we have to figure out like what's the better connection to make. And so let's say we have like these two groups, right? This group has a parent of x, this group has a parent of y, and we decide to connect it where y becomes the parent of x. So this is like the new parent. Y is new parent. So then all we have to do is just say, okay, we'll make the y the parent of x, and then the size of y will be the old size of y plus the size of x. So this will be the size of y. And then we're just going to loop through every single node that we have and check, is it its own parent? And that means it's the parent of the whole group, and that'll be its size. That's basically what I did here. So I just said, if y is going to be the new parent, then we're going to add the size of x to the size of y. If x is going to be the new parent, then we're going to add the size of x to the size, or the size of y to the size of x. You do the same addition, but then we're, like I said, we're only going to look at a few nodes that their parent is itself. So yeah. And then we have this function that I made that just gives you the size of something. Gives you the size of a node. And so it basically just gets the parent of the node. This is like totally not necessary. You can just say, like, for every node, call find. If the find is the same, then give me size. The only reason I did that is because this is a private variable, so it'll give it to you. But if you want to access it directly, you can access it directly. So yeah. And then we basically get the stone's length. We call our union find. And then, so I talked about this before. In Java, you're going to want to use arrays when possible. So I just said, let me make rows from 0 to 10,000 because those are the constraints. The value can be from 0 to 10,000. You can use a hash map here if it makes more sense. And fill out every value with -1. Then we're going to go through everything and we're going to get the row and the column. We're going to check, is the row value -1? If it's -1, that means there's nothing here. And if it's not -1, then we have something we could do a union with. So if there's nothing here, we'll set this index to the row. And if there is something here, we just do a union. Same thing here for the column. If there's nothing here, you set it to the column. And if there is something, you do a union. Then we just go through every single node and we check, is the node its own parent? If it is its own parent, that means it's the parent of the group. So we don't want to like count duplicates. So we just want the parent of every group. And if we have the parent of the group, we just add that parent's group size -1. Because we're going to be able to get rid of every single stone in the group, -1 for every group that we have. And then just returning. That's basically it. So not super bad. And you can see that even though we initialize to like a really big number, it's still faster with arrays in Java because there's less overhead. So something to think about. Okay, so time here. So the way we did our solution is we did set the rows and columns to this like 10,000. So I guess we can just say like this is 10,000 or like the stone, like max stones or something. But basically, yeah, it'd be like stone value, whatever you want to call it, because we hard coded this value in. And then for union find, all the find and union operations are roughly O of 1. They're like 1.2 or something. So basically rounds down to O of 1. And then so we make these rows, we make these columns, we do this fill. So that's basically O of like this 10,000. And then we go through every single edge, or not edge, every single stone. So let's check here really quick. Yeah, so stone's length is 1,000. So it's basically like, it'll basically be capped to this because stone value is 10,000. So you can say it's like O of 10,000 if you want to. That's pretty accurate because this value is always going to be less. Yeah, so you could say probably something like this is like, because we hard coded it, this is O of 10,000, this is O of 10,000. So if those are constant and we ignore those, then it's going to depend on the stone's length, so then it'll be like n and n if you want to write it like that as well. Either way, it's fine. But yeah, hopefully that makes sense, and if it does, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.